Okay, so this is the first meeting of the mini-course on operational quantum reference frames. Okay. The purpose of today is to set up the mathematical preliminaries. So it's not gonna be about quantum reference frames yet, and this is gonna come next week. But it's gonna be about infinite dimensional quantum mechanics, and if time allows, also GPTs in infinite dimension. So there was already a question here. Why do we need to this generality? So why cannot we just do quantum mechanics with matrices on infinite dimension? And well, my take on this is that well, as will become clear next week, I will need to group representations, and the groups that I will represent, they're non-compact, and therefore there are no representations, no unitary representations of them in finite dimension. So to make formal sense of the tools that I need to care about infinite dimensional Hilbert spaces. Yeah, you may not like it, that's fine. I think also, so many people say that restricting to finite dimension helps us to get rid of the technical problems of quantum theory and focus on the conceptual problems. And I highly disagree with this view. So I think it's actually the opposite. So, I mean, of course, you need more technical tools to deal with infinite dimensions. But I think that taking care of this, well, in a way, this infinite dimensional setup is more demanding in terms of being precise which objects live in which spaces and distinguishing between them. So in finite dimension, basically everything is a matrix, and it's very simple to confuse notions, while in infinite dimension we are forced to be very careful in defining well, everything. So I also like mathematics, so that's part of the reason why I do this. But I also think it's useful and maybe also necessary for some things. Okay, so let me start. I will start with some motivation for the whole program, but then dive into the technical setup. So quantum field theory lies at the basis of physical theories that we construct, also quantum gravity theories, where we usually try to quantize something. And in my view, this is not fully satisfactory as a framework for physics as we know it, for various reasons. Among them, well, it's been over 100 years and we still don't have any rigorous formalization of interacting quantum field theories, which maybe it's just a matter of time, but maybe it's time to also look for some other things. Then quantum field theory is dependent on fixed background space-time geometry. We can do quantum field theory on curved geometries.
Sorry.
It's fine. Yeah, take a seat.
Can I join this?
Of course.
Because today I was told about this.
Yeah, that's fine. So we are being recorded, so just so you know. So take a seat and enjoy. So we just started. Today is mostly about the technical setup, so infinite dimensional quantum mechanics. But I just started with some motivation why I want to pursue this program of operational quantum reference frames. So I start with some points of dissatisfaction about quantum field theories. Maybe I can add, what are you working on? Just to sentence.
General classicality of bosonic fields.
Okay.
And also a little bit in some, I think, similar topic, but not the same, like quantum information without shared reference frames.
Okay.
Especially in the without relativistically invariant encoding. So.
Amazing. Okay. Cool. So you know the problems. And you?
Yeah, I work with well, say now on the cross-section between quantum cryptography, quantum Darwinism, and trying to now analyze these from the perspective of quantum Darwinians, how is the security, given what the security of quantum key distribution, given what Jurek has written in his many papers.
Jurek guy. Okay, cool. Thank you. So this framework we will get to next week is starts with work of Leon Loveridge, starts from quantum measurement theory, and then goes into the direction of the ideas of quantum reference frames. Okay, but let me not go ahead of time. So I'm just complaining about quantum field theory, that they're not rigorous enough and that they are background dependent. And they compromise operationality and relationality. And what I mean by this is that, I would like, what the operationality I have in mind here is basically a theory is operational if it is a straightforward way to go from the abstract notions of your theory to the actual measurable predictions. If this process is straightforward and simple, I would call it theory operational. Otherwise, maybe not so much. So in quantum field theory, it is a long way from the setup of these classical fields that we try to quantize to the S matrix formalism and what we can actually try to measure there. So I think maybe there is a cleaner way to speak about quantum theory in the relativistic realm, more operationally. And relationality is I think is a very deep principle, even you could demand from a physical theory, which basically takes care of the fact that whenever we make an observation, there is another physical system involved that is your apparatus that you use, and it also serves the role of a quantum reference frame in this setup. So we will treat an apparatus of quantum measurement theory as a quantum reference frame. We'll put some symmetries on top of it and speak about relative degrees of freedom, this kind of stuff, next week. So these are the complaints about quantum field theory, that I don't think it's operational enough or relational enough. So there's no mention of any measuring instruments in the setup. There's been some progress in quantum measurement theory in quantum field theory recently, and I'm not gonna go there, but there is some possible intersection between the ideas that I'm gonna talk about and this program. Actually, people are already working on this. So the goal would be to provide something better, something that would be rigorous, background less, operational and relational in the senses that I briefly described, and powerful enough to capture relativistic quantum physics and maybe also some more general things. So that's the dream. We're not gonna do this now, but we start from scratch. So today I would like to do these two things. So I think we try to have a break around 5, just to be keep fresh. So first I will really start from the basics of infinite dimensional vector spaces, Banach spaces, Hilbert spaces, and then bounded operators. These are basic objects I will care about. And then I will speak about quantum mechanics, how this is done, elementary, what we do also in finite dimension, and what are problems with this standard elementary textbook approach to quantum mechanics. Then I will advertise how we can fix these problems, and then if we have time, I will speak about more general probabilistic theories. All right? Okay. Any questions you have, you just ask them. Okay, we have time. We don't have to go through all this. It's more important that we are on the same page next week than we just. I know what's on this slide, so it's not for me. Right. So Banach spaces. So first, okay, and also if something is too elementary, too simple, everyone knows this. You just say this and we skip and go further. So. The point is that, in general, how this can be seen is that we know this three-dimensional Euclidean space that we seem to be surrounded by, at least locally. And mathematicians have been working a lot into generalizing these notions into, well, generalizing them to some more general things. So the most general object I will mention is a vector space. So it's just a set of these two operations. So we can add vectors and we can scale them. We can multiply them with numbers, and numbers come from the field, and the field is gonna be real complex numbers. That's a basic definition. And so this, well, in R3, I will try to give some examples. So in R3, well, basically, if you have vectors that are represented on a plane with these three numbers, and then you can add them and multiply like this. So the idea is to generalize this kind of operations to, well, abstract sets. Okay, and what is a normed vector space? Is a vector space on which we have a norm, and a norm is a map that gives you a number for any vector, and this number has to be non-negative and not infinite. So basically this should be thought of as the length of the vector, and this map has to satisfy some properties. So if the length of the vector is 0, then the vector itself is 0. It will scale properly when we multiply vectors by numbers, and the triangle inequality will hold, which is this thing. So this generalizes the length in R3. In R3, this is given by the Pythagorean theorem, and the triangle inequality is the one that we know from school. Well, on the plane, probably. When we have a norm on our vector space, it induces the notion of a distance. So we can subtract one vector from another because it's in a vector space, and then we can calculate the norm of this. And if the vector so this gives us a notion of how far one vector is from another, which is a distance function or a metric. So the next notion we need is a metric space. If I go too fast, please let me know, or if I go too slow as well. Right, metric spaces. So a metric space is a set with a metric. So now it's a function that takes two elements of a set and gives you a non-negative, non-infinite number. So, and it has to also satisfy some properties. So if you want to calculate a distance from point to itself, it should be 0, and it's a symmetric function, so it's as far from P to Q as it is from Q to P. And the triangle inequality, which is now something else, but is equivalent if this metric comes from the norm. Okay. So in Euclidean space, again, the metric, the distance function, is this sort of thing. So we just apply the Pythagorean theorem. Yeah, fine. And why we need this? Well, part of the reason is that in a metric space we can speak about sequences and limits. Because we can say how far things are one from another. So we will be interested in sequences of elements of these metric spaces. So let's say a sequence is just a labeled family of elements, arbitrary. And some sequences can have limits, and the limit is another point in the space that for the elements with high indices, they're gonna be very, very close, as close as you want to this limiting point. And so formally, we say that an element is a limit of a sequence if for any positive number. So the idea is that this epsilon is small. There is a natural number such that for elements with higher indices, the distance between the limiting point and the one is arbitrarily small. And this element is denoted as a limit. And why is this interesting? We will see in a minute an example that you're very familiar with, and maybe this will help. Because so there is a class of sequences which are called Cauchy sequences that we would expect that will converge, and then we will be interested in such metric spaces for which these special sequences actually converge, and so they have limits. We'll call them complete. So a Cauchy sequence is such that when you check distances between elements of your sequence, if the indices are high enough, the elements get closer and closer to one another. That's the idea. So intuitively speaking, well, okay, we can write it down with the epsilon, but maybe there is no need. Intuitively speaking, we will expect this thing, this limit to exist in our space. Otherwise, it seems like there is like a hole in our space, because we cannot get there. We can get as close as we want, but we cannot get to the point, so to say. So a metric space, we call it complete if all such Cauchy sequences converge. And an example is the real numbers, which can be the set of the metric space of real numbers, which is also a vector space and everything you want. It can be seen as a completion of the rational numbers. So we can have a sequence of rational numbers converging to any real number, but the limit may not be a rational number anymore. But if we take this completion, we get to the reals. And this is gonna happen all the time. I will take, like next week, we will take like complete spaces. Yes, and now the definition. So what is a Banach space? A Banach space is a complete normed vector space. So to recap, we have a vector space over the reals or complex numbers. We have a norm. This norm defines a notion of a distance, and we can check if the Cauchy sequences converge, and if they do, then it's a Banach space. It's a pretty basic object in a way. It's very, very general, so many spaces in mathematics are Banach spaces, but it's also powerful enough that you can prove general theorems about Banach spaces.
What do you mean by dense?
Okay, here. How to best say? Well, precisely that when you take a completion, you get the whole thing. So you have real numbers, they are a set, and the rational numbers, they are a subset.
Right.
But when you complete this subset by adding the limits of sequences, you get the whole thing. This means that the subset is dense.
Okay.
There could be some other.
The set which is completable. So it can be completed by
so being
extension.
dense is a property of a subset.
Mm-hmm.
So when I have a whole space like reals, I can pick a subset, and it can be dense or not. And if I add the limits to this subset, and if when I do this I get the whole thing, this means that the subset is dense.
Right.
You could have
so
like
any subset
Uh-huh.
which I mean let's say first you consider the rational number set,
Yes.
and then you say that okay, so I can add some elements into it and I can complete it.
Yes.
So that is why the set of rational numbers is dense.
Exactly. Yes.
Yeah.
Okay. Any other points? Okay. So we already know what are Banach spaces. This is good. Maybe yeah. Okay. So what are Hilbert spaces? So it's in finite dimension we know this is like complex numbers to some power, but in infinite dimension this is more complicated, more interesting as well, I think. So let's see how we define. So we have a notion of an inner product on a vector space, which is a map that again satisfies some properties that you surely have seen before. So it is when you replace the order of the vectors that you put. So it's a map that takes two vectors and gives you a complex number, and if you reverse the order of the things, you get the complex conjugate. As a result, it is linear in the first or in the second. I mean, there is a convention, but you have to pick one. So in one slot it's linear, in the other slot it has to be antilinear due to the first condition. And then we also need that when you take an inner product of a vector with itself, it has to be positive. and if it is 0, then we should be able to conclude that the vector was 0 itself. So a vector space with an inner product is an inner product space. All right. So this is again something that generalizes some sort of structure from the real Euclidean space. So in 3 dimensions we have, so this is a real vector space, we have this sort of inner product, which has to do with the norms of the vectors and the angle between them. If we have an inner product, we also have a norm. We can define a norm by saying that the length of a vector squared is the same thing, is defined by the inner product of it with itself. So this is a general feature. We can do this anytime we have a inner product space, and then a Hilbert space is an inner product space that is complete in the norm that is defined with the inner product by this last equation. All right. So we start. Yeah, I said. So the simplest non-trivial example is just complex numbers, where we have the inner product just this, and it generalizes to arbitrary dimension by this simple formula. So, and all finite dimensional Hilbert spaces are basically of this form. So these are just complex numbers. Now we will need a notion of a basis, orthonormal basis, and we will only consider countable orthonormal basis. So it's a set of vectors, countable set, and each of the, if you calculate the inner product of any pair of vectors, it should be 0. They're orthogonal, and it has to the set has to satisfy this property that for any vector in a Hilbert space, it can be written as a sum. This sum can possibly be infinite if the dimension is infinite, as this sort of sum. So you take the inner product, you sort of project to one of the directions, and you have this this sum. So the dimension of a Hilbert space is the smallest, the number of the minimal number of orthonormal bases, and it can go to infinity. Such Hilbert spaces are called separable, that admit this sort of orthonormal basis. It could happen that there is an abstract Hilbert space with no such basis. They're called non-separable then, and they're not. Well, some people worry about those in the context of quantum field theory, but in the standard like quantum mechanical setup, the Hilbert spaces that we encounter are separable. Okay. Cool. Bounded operators. Where are we going with time? Cool. Bounded operators. So when we have a Hilbert space, we can think about linear operators, so maps from H to itself that are linear. And we can consider a space of these things called L of H, linear operators. It is always a vector space because we can add them and multiply by numbers according to these formulas, which are pretty straightforward. And then we can also put a norm on this space. So a norm of an operator is the maximal number that can be achieved by evaluating it on vectors, calculating norms. So you can, this formula can be written in many different ways. So you can also say that the norm of psi is 1, and then you don't have to divide. You've seen this before, I'm pretty sure. And then among the linear, so in finite dimension, every operator has a finite norm, but it's not the case in infinite dimension. So we define a subset of these linear operators for which this norm is finite, and we call them bounded, and this is the space, the famous space of bounded operators on a Hilbert space. This set has more properties. So because they are operators, we can compose them, and since the composition of two bounded operators remains bounded, we have an algebra structure on P of H, which means that we can see it as an operation that takes two operators and gives you a second one, and this is a non-commutative operation in general, which means that when I replace them I get something else. And moreover, because of the Hilbert space that's underneath, we also have the adjoint operation. So for any bounded operator, there is exactly one A star here that satisfies this equation, and therefore, and it's also bounded, so we can see this as another map, structure map on this space that takes A and gives you the adjoint. So yeah, well, all of this, so it's a Banach space, you can multiply things and take the adjoint. This is called a star algebra, and there is also a special relation between the star operation and the norm that makes it a C-star algebra. And why people care about these things is, well, one of the reasons can be that any C-star algebra is always basically of this form, so it's a subalgebra of some P of H. So we're very close. We don't need it, so I don't go there, but we're very close to like abstract algebraic characterization of this quantum mechanical setup. Yeah. Any questions here? Okay. So it will be useful to consider special classes of bounded operators. So we say an operator is unitary if it preserves the inner product, which is just this. So it may be useful, but maybe not if you're familiar with the Hilbert spaces, and perhaps not, but you may want to have in mind the simple case of just complex numbers. So bounded operators on the Hilbert space that is one-dimensional, so on complex numbers, are just complex numbers again. So we can speak about all these kind of things. And the unitary operator in this case is just a number of norm 1, so e to I phi. So they form a group, and they're nice and simple. Self-adjoint operators are such that A is a dagger, a star. So in the complex number case, these are just real numbers. An operator is positive, so there are different definitions that are equivalent. I like this one because it's very general. So an operator is positive if it can be written in this form. So we can see it is already self-adjoint, because when you take an adjoint of this, then it's the same. And it's equivalent to having the real spectrum, a positive real spectrum. Projections are self-adjoint and idempotent. So yeah, it's again, and yes, I don't think something interesting can be said here. Trace class, this is an important notion. So in finite dimension, every operator has a finite trace, but in infinite dimension, it is not clear if the trace can be defined. It turns out it can, because for any choice of an orthonormal basis, you can consider this sort of sum, and it turns out to be independent of the choice of the basis. And for some operators, this will be finite, and we call them trace class operators. They will be important. They form a Banach subspace and on its own, and we'll see them coming back. Okay, any questions? Cool. Okay, then we move to quantum mechanics. We can perhaps do this already. So when you first learn about quantum mechanics, this is more or less what you get. At least that was the case for me. Maybe you have better education here. So states are just this sort of kets, and to define them properly, they are arrays in a Hilbert space, so classes of unit vectors with the equivalence given by the phase. So that's pretty standard, and the idea is that nothing should depend on this face, which is okay. And then observables are defined to be self-adjoint operators, bounded self-adjoint operators. Maybe, well, obviously this is not good enough, but this is where we start. And we also think about them as generating an orthonormal basis of eigenvectors. So there should be a set of vectors labeled by natural numbers, such that when you act on them with the operator, you just get the same thing scaled. And this eigenvalues, they should be real. Well, they will be real if A is self-adjoint. And this is we need all these things in this basic setup to speak about probabilities and everything else. So I'm gonna just run through how this happens, and then I'm gonna argue why this is not good enough and how to fix the problems. The first problem is already that a self-adjoint operator on an infinite-dimensional Hilbert space may not have any eigenvectors, and then you cannot do anything with it. That's like the first just note that maybe we should go and look for something better if we care about infinite-dimensional Hilbert spaces. So first thing, such an operator can be written as a sum. So we need to remember this formula because it's going to be generalized later on. So this lambdas, they are eigenvalues, and P are the projections into the subspaces spanned by eigenvectors. Because there can be more than one eigenvector that gives the same eigenvalue. So their projections, they don't have to be one-dimensional, but they're certainly projections. And then if it has this spanning set of eigenvectors, it can be written like this. Basically, if it's a matrix, you just diagonalize it, and you do it every day, perhaps. And then expectation values, they are these things, and if you evaluate them on the eigenvectors, you get the eigenvalues, obviously. And since the eigenvectors, they form a basis, you can do a similar thing with any vector. You just write it down in the basis, and you get this formula. Okay, this is actually wrong. There should be a square here. Okay, wait. Maybe we do a break now, and I fix this. Is that fine?
Yeah, sure.
Yeah, this is okay. Then 5-minute break. I will see if the recording is going. Okay.